Somewhere off the coast of southern China, there's a road that doesn't end where the land ends. It keeps going past the beaches, past the last visible shoreline, out over open ocean, where the water is deep enough to swallow a 10-story building and the wind is strong enough to flip a truck. And then, just when it looks like the road is about to run out of ocean to cross, it disappears completely, diving underwater through a tunnel resting on the seabed so the largest ships on Earth can pass overhead without ever knowing a highway is running beneath their hulls. This isn't a bridge. It's barely even a road. It's one of the most extreme pieces of engineering ever attempted by human beings. Built to survive a magnitude 8 earthquake, a category 16 super typhoon, and a direct hit from a fully loaded cargo ship, all at once, if it had to. Even American engineers, the people behind the Golden Gate and the Brooklyn Bridge, looked at the blueprints for this thing and said it couldn't be done. Not in this ocean, over this seabed, in this amount of time. China built it anyway. In a few minutes, you'll understand exactly why nothing like it exists anywhere else on the planet. Before we go further, drop a comment. Where in the world are you watching from, and what time is it there? Hit subscribe if you're new here. This is where the world's most extraordinary stories come alive. Now let's begin. To understand why this crossing is considered one of the hardest engineering problems ever solved, you have to understand the stretch of water it crosses. The Pearl River Delta is one of the busiest, most dangerous, and most economically important bodies of water on the planet. It connects 3 of the world's most important cities: Hong Kong, Macau, and the mainland city of Zhuhai. For decades, the distance between them wasn't measured in kilometers, but in hours. A container truck moving cargo from Zhuhai to Hong Kong had 2 choices: drive nearly 4 hours around the entire delta on congested mainland roads, or load the cargo onto a ferry and hope the weather held. There was no direct route, not because nobody wanted one, but because nobody believed one was possible. The distance to cross is roughly 55 kilometers of open water, more than 34 miles, longer than the entire length of Manhattan, repeated over 20 times in a row. For comparison, the Golden Gate Bridge, the bridge most Americans picture when they think of a great bridge, is less than 3 kilometers long. This crossing needed to run almost 20 times that length, over open sea, not a calm bay, and the water itself was hostile. This stretch of the South China Sea sits directly in the path of some of the most violent typhoons on Earth, with wind speeds during a direct strike exceeding 250 kilometers per hour. The seabed beneath the water is soft marine clay in places, capable of swallowing a badly designed foundation over time. And running straight through the middle of the crossing zone is one of the busiest shipping lanes on the planet. Hundreds of massive cargo vessels, some carrying over 20,000 containers, passing through every single day. Any bridge built across this water would need to be tall enough to let those ships pass beneath it. But the shipping lane also happened to sit directly beneath the approach path for Hong Kong International Airport, one of the busiest airports in Asia. A bridge tall enough for ships would be too tall for planes on final approach. This is exactly the kind of problem where most countries would simply declare the crossing impossible and leave it as a permanent ferry route. China's engineers looked at that same problem and designed something almost nobody outside the country believed could work. A bridge that turns into a tunnel in the middle of the ocean, with no visible seam where one method ends and the other begins. Here's the part that made engineers in the West stop and look twice at the plans. For most of its length, the crossing is a 6-lane bridge, resting on massive concrete piers driven deep into the seabed. But as it approaches the busiest section of the shipping lane, the bridge does something almost no infrastructure project in history had attempted at this scale. It sinks. The roadway descends onto 2 artificial islands built specifically for this purpose, and between those 2 islands, it disappears entirely underwater, becoming a 6.7-kilometer undersea tunnel, over 4 miles of roadway, sitting on the ocean floor. Deep enough that the largest container ships in the world can pass directly overhead with room to spare. Think about what that actually requires. You're not digging a tunnel through solid rock the way engineers usually do. You're assembling it piece by piece, directly on the seabed, in a stretch of ocean known for violent storms and shifting currents. The tunnel was built using 33 individual concrete segments called immersed tube sections, each roughly 180 meters long and weighing around 80,000 tons, heavier than the Eiffel Tower, repeated 33 times. Each one sunk into position on the ocean floor with a margin of error smaller than the width of a human hand. Every one of these segments had to be built on land, floated out to exact coordinates, sunk with millimeter precision, and sealed against its neighboring segments, so not a single drop of seawater could ever find its way inside. If even one of these seals failed at depth, the consequences wouldn't just be an engineering failure, they'd be a catastrophe, with a 6-lane highway sitting directly beneath the ocean. American engineers who reviewed early details of the project openly questioned whether this level of precision was even achievable at this scale, in open ocean conditions, on a construction timeline this aggressive. The immersed tunnel techniques that existed before this project had never been attempted at this length, this depth, or in waters this exposed to typhoons, towering waves battering massive artificial islands sitting right in the center of a typhoon corridor. China's engineers didn't just prove it could be done. They finished the tunnel with a level of sealing accuracy that surprised international engineering observers. Reportedly, essentially zero leakage, with not a single one of the 33 segments requiring significant rework after installation. An outcome many experienced tunnel engineers considered close to unbelievable for a project of this scale. Building islands that didn't exist. New land where there was once only water. This is the future of infrastructure. Before the tunnel could exist, the two islands anchoring it had to exist first, and neither of them was there to begin with. Engineers needed solid ground in the middle of open ocean, in water up to 44 meters deep in places, on a seabed made of soft marine mud that couldn't support a foundation the traditional way. Traditional land reclamation, slowly dumping rock and sand until an island rises out of the water, would have taken years, and the project's timeline simply didn't allow for that. So the engineering team designed something that had never been used at this scale anywhere in the world. Enormity. Hollow steel cylinders, some as tall as a 20-story building, driven directly into the seabed like giant drinking straws pushed into wet sand. A total of 120 of these steel cylinders were sunk into position, forming a solid ring. Once locked into place, the interior was filled in, creating a stable artificial landmass capable of supporting roads, tunnels, and buildings. Built in roughly a year, a process conventional reclamation methods would have taken several times longer to achieve. This technique, known as the large diameter steel cylinder method, had never been attempted at this depth or scale anywhere in the world before this project. It was designed specifically because nothing that already existed could solve the problem fast enough or strongly enough for what this crossing demanded. Designed to survive the end of the world, every part of this crossing was built around a single number, 120 years. That's how long the structure is engineered to last, more than double the design life of most major bridges built anywhere else on Earth. Including in the United States, where the average major bridge is designed for a lifespan closer to 50 to 75 years. To hit that number in this specific location, engineers had to design for the absolute worst-case version of nature. The bridge and tunnel system is rated to withstand an earthquake measuring 8 on the moment magnitude scale, strong enough to rank among the most powerful earthquakes ever recorded. It's rated to withstand a super typhoon with sustained winds strong enough to sit at the very top of the tropical cyclone scale, a storm intensity that would shut down entire cities and ground every flight in the region. And in a detail that stunned engineers when it was first published, the bridge's piers were designed to survive. A direct collision from a 300,000-ton cargo vessel traveling at full speed, roughly the weight of the largest oil tankers on Earth, without the structure collapsing. For comparison, most Western bridges are engineered around a maximum design. A vessel far smaller than that, because a collision from a fully loaded supertanker is considered such an extreme, unlikely event that most bridge designs elsewhere in the world simply don't plan for it. In the Pearl River Delta, with hundreds of massive ships passing daily, engineers treated it as a scenario they had to design for, not around. Numbers this large are genuinely hard to picture, so here's what the finished project actually required. More than and currents can shift without warning. A category of construction work ranking among the most physically demanding engineering labor performed anywhere in the world. And for decades, it was considered one of the most ambitious engineering feats in American history. But scale changes everything. The Chesapeake crossing runs a little over 28 kilometers. This Chinese crossing runs 55 kilometers, almost double the The honest comparison isn't that China did it better than the engineers who came before. It's that China took a Western engineers off guard. It isn't that the idea was new, it's that nobody else had been willing or able to build it at this scale, in this amount of time, in water this dangerous. So what actually changed? Before this crossing existed, moving goods between Zhuhai and Hong Kong by road meant a trip of nearly 4 hours around the delta. After it opened, that same trip dropped to under 30 minutes. For a region responsible for a staggering share of global manufacturing and shipping output, cutting a 4-hour trip down to 30 minutes isn't just a convenience. It restructures how an entire economic region functions. Factories in Zhuhai gained faster access to Hong Kong's port and airport. Logistics companies redesigned entire supply chains around the new travel time. What used to be 3 separate economic zones, functionally isolated by water, began operating as one connected region. This is the part that rarely makes it into headlines about the world's longest sea crossing. The engineering is what grabs attention, but the economic transformation is what actually justified spending years and enormous resources building it. The part even critics couldn't argue with. No mega project of this size comes without controversy, and it's worth being direct about that rather than pretending otherwise. The project faced real criticism during construction, concerns over worker safety, incidents, cost overruns beyond original budgets, and questions from environmental groups about the crossing's impact on the local population of Chinese white dolphins living in the delta. Engineering teams responded by adjusting construction methods and timelines to try to reduce disruption to the dolphin population, including altering piling schedules and installing monitoring systems, though environmental groups continued debating how effective those measures actually were. But what even the harshest critics of the project's cost and process didn't dispute was the underlying engineering achievement itself. When news in other countries planning their own extreme sea crossings. That's the detail that tends to surprise Western viewers most. This wasn't just China building something big, it was China solving an engineering problem that had stopped other countries from attempting a similar crossing anywhere else in the world at this scale, how it stacks up against the world's other giants. To really understand what this crossing achieved, it helps to line it up against the other legendary bridges people already know. Japan's Akashi Kaikyo Bridge, connecting Kobe to Awaji Island, held the record for the longest. Suspension bridge span in the world for decades and remains one of the most respected engineering achievements in Asia. It stretches just under 4 kilometers. This Chinese crossing runs 55 kilometers, roughly 14 times longer, though it uses a completely different combination of bridge, island, and tunnel engineering rather than a single suspension span. Denmark's Great Belt Fixed Link, connecting 2 of the country's main islands, was considered one of the most ambitious sea crossings in Europe when it opened in the late 1990s, combining a suspension bridge and undersea tunnel across roughly 18 kilometers of water. For years, it was one of the closest things in the Western world to what this Chinese crossing eventually became, accounting for roughly a third of the total length, and without the same earthquake and super typhoon design requirements. Even the Øresund Bridge, the striking bridge tunnel connecting Denmark and Sweden that most people recognize from film and television, spans just under 16 kilometers total. It's a genuinely elegant piece of engineering. It's also less than a third the length of the crossing this documentary is about. None of this is about declaring a winner. Every one of these projects solved a real problem for the country, that built it under real constraints, with the technology available at the time. But when American and European engineering commentators reacted to the completed scale of this Chinese project, the consistent response wasn't disbelief that China could build a bridge. It was disbelief that anyone had found a way to combine every one of these separate engineering challenges: suspension-level span distances, immersed tunnel technology, artificial island construction, and extreme disaster resistance requirements into a single 55-kilometer structure on a construction timeline measured in years rather than decades. The people who never saw daylight, the engineering numbers tend to dominate the conversation, but underwater construction at this scale ultimately comes down to human beings doing extraordinarily dangerous work far from any camera. The specialized diving teams responsible for guiding each of the 33 tunnel segments into place worked in conditions most people would find almost unimaginable. Visibility at the required depth could drop to near zero from sediment stirred up by currents. Divers used precision instruments to guide segments weighing tens of thousands of tons into alignment, working to tolerances smaller than a few centimeters, fully aware that a miscalculation at that scale wasn't a minor error. It was a project-ending failure. Engineers on the surface described sealing each tunnel joint as one of the most tense phases of the entire 9-year build. Every one of the 33 seals had to hold under enormous water pressure indefinitely for the structure to be considered safe for public use. There was no way to fully test a seal except to complete it and monitor it under real conditions. This is the part of megaproject engineering that rarely makes it into headlines about world's longest or world's biggest. Somewhere beneath the surface of the South China Sea, ordinary construction workers and engineers spent years solving a problem that had never been solved at this depth or scale anywhere on the planet, and very few of them will ever be publicly recognized for it. Standing at the midpoint, picture standing on one of the artificial islands at the exact point where the bridge disappears into the tunnel. Behind you, 6 lanes of traffic stretch back toward the mainland, elevated high enough above the water that a typhoon could be raging beneath you and you'd still be safely above the worst of it. In front of you, the road simply vanishes into the ocean. No ramp warning you, no sign announcing it. The highway just goes under. Island stays under for more than 6.5 kilometers, while some of the largest ships ever built pass silently overhead. There's nowhere else on the planet where you can stand in that exact spot and feel both of those realities at once. A bridge built to survive an earthquake capable of leveling cities, and a tunnel built to let you disappear beneath a typhoon while it destroys everything on the surface above you. Somewhere off the coast of southern China, there's still a road that doesn't end where the land ends. It survived 9 years of construction, 120 steel cylinders sunk into the seabed, 33 tunnel segments sealed by hand at the bottom of the ocean, and a design standard built to outlast almost every other bridge on Earth. And it's still out there right now, carrying traffic across 55 kilometers of open water, disappearing beneath the waves exactly where the largest ships in the world need to pass. Proof that the hardest engineering problems on the planet aren't actually impossible. They're just waiting for someone willing to build the answer.